Greetings, AP Stats students. Today we're going to be looking at, starting at Chapter 10, comparing two populations or groups. Basically, this chapter consists of two sections. We're going to compare two proportions first, and then we're going to compare two means in 10.2. Unlike previous chapters, though, we are going to be looking at doing both kinds of inference that we've talked about. That is confidence intervals and significance test in both sections. We're going to do it today with two proportions, and then in 10.2 we'll do it with two means. So, to get started here, our objectives for today are, after this section, you should be able to describe the shape, center, and spread of the sampling distribution of the difference of two sample proportions. You should be able to determine whether the conditions are met for doing inference about P1 minus P2. And then you should be able to construct and interpret a confidence interval to compare two proportions and perform a significance test to compare two proportions. All right, so introduction. Suppose we want to compare proportions of individuals with certain characteristic in population 1 and 2. Let's call these parameters of interest P1 and P2. The ideal strategy is to take separate random samples from each population and to compare the sample proportions with that characteristic. What if we want to compare the effectiveness of treatment 1 and treatment 2 in a completely randomized experiment? This time the parameters P1 and P2 that we want to compare are the true proportions of successful outcomes for each treatment. We use the proportions of successes in the two treatment groups to make the comparison. Oops. So you got population 1, population 2. Each of those had their parameters, P1 and P2. The statistics, P hat 1, or P hat 1 and P hat 2, and sample sizes N1 and N2. Okay, so two different populations here totally. All right, so the sampling distribution of a difference between two proportions. To explore the sampling distribution of the difference between two proportions, let's start with the two populations having a known proportion of successes. At school 1, 70% of students did their homework last night. At school 2, only 50% of students did their homework last night. Suppose the counselor at school 1 takes a simple random sample of 100 students and records the sample proportion that did their homework. School 2's counselor takes a simple random sample of 200 students and records the sample proportion that did their homework. What can we say about the difference P hat 1 and P minus P hat 2 in the sample proportions? Well, using some software here, they use some stat software here. They generated a simple random sample of 100 students from school 1 and a separate simple random sample of 200 students from school 2. The difference in the sample proportions was then calculated and plotted. We repeated this process 1,000 times. So as you can see here, you've got the first one had a center of 0.7, the second one had a center of 0.5, and the difference had a center of 0.2. So obviously they subtracted. They took the mean of the first one minus the mean of the second one to get the mean of the difference. The spread is not as obvious there, but you've got the spread values there. And then they calculated the standard deviation of those values for the spread there. And then you got the standard deviation of the actual difference at 0.058. It's not as obvious what they did right there to get that. However, we have done this before, actually. You just don't realize it. Maybe yet. So what do we notice about the shape, center, and spread of these distributions? Well, let's look at the spread. This one looks like it's pretty normally distributed. You got a single peak, bell-shaped curve, single peak, bell-shaped curve, and the difference is also single peak, bell-shaped curve. Funny. So both P1 and P2, or P hat 1 and P hat 2, are random variables. The statistic P hat 1 minus P hat 2 is the difference of these two random variables. In Chapter 6, we learned that for any two random variables, x and y, the mean of x minus y was the mean of x minus the mean of y, and the variance of x minus y was the variance of x plus the variance of y. The Pythagorean theorem of statistics. It's back. So this is how you can calculate that. We have to take this, of course, the variance is the standard deviation squared. Don't forget that. So choosing a simple random sample of size N1 from population 1 with proportion of success as P1, and an independent simple random sample of size N2 from population 2 with proportion of success as P2, the shape when N1, P1, N1 times 1 minus P1, N2, P2, and N2 times 1 minus P2 are all at least 10, then the sampling distribution of P hat 1 minus P hat 2 is approximately normal. You have to check both of those conditions. These conditions again. It's still the NP and N times 1 minus P, but now this time we have to do it for both population 1 and population 2. We have to check that to make sure that both sampling distributions are or check both of those actually to make sure that the sampling distribution of P hat 1 minus P hat 2 is approximately normal. The center then of that sampling distribution will be P hat 1, or I'm sorry, P1 minus P2. And the spread, the standard deviation of P hat 1 minus P hat 2 is the square root of P1 times 1 minus P1 all over N1 plus P2 times 1 minus P2 all over N2. Now, it may not be as obvious, but you'll recall that the sampling distribution for P hat had the square root of just this first part right here. Well, the sampling distribution of P2 or P hat 2 would be the same thing, but just with P2s. When you plug those into this formula right here and do the Pythagorean theorem with them, you're squaring those individual square roots and then putting them underneath a big square root. So this square root is the big square root, whereas you would put the smaller square roots underneath that one and you squared them. So that's why there's not a square roots on each of these individual standard deviations here. It's because you ended up squaring them anyways. So you squared the square roots. Those individual square roots went away, but you have them all underneath the big square root at the same time. I know that's a little confusing. We may look at that again tomorrow for me to show you how that comes about. Regardless, these formulas are on your formula sheet. They're on your pink formula sheet, so they're there for you. This is, of course, as long as each sample is more than 10% of its population, you have to check the 10% condition. All right, so you got your sampling distribution of P hat 1 minus P hat 2. It has a mean of P1 minus P2, and it has a standard deviation, this right here, this big blob mess. Suppose that there are two large high schools, each with more than 2,000 students in a certain town. At school 1, 70% did their homework last night. Only 50% of students at school 2 did their homework last night. Counselor at school 1 takes that simple random sample of 100 and records the proportion that did homework, and school 2's counselor takes a simple random sample of 200 students and records the proportion that did homework. Describe the shape, center, and spread of P hat 1 minus P hat 2. Well, N1 P1, that would be 100 times 0.7, that's 70. And N1 times 1 minus P1 would be 30. Both of those are more than 10. N2 P2 would be 200 times 0.5, which is 100. And the other one would be 100 as well. And all of those are at least 10. So the sampling distribution of P hat 1 minus P hat 2 is approximately normal. Its mean then would be P1 minus P2, which is 0.2. And its standard deviation would be this. We would plug all that in and calculate that. It comes out to be 0.058. That's where that came from. So, confidence intervals for P1 minus P2. When the data comes from two random samples or two groups in a randomized experiment, the statistic P hat 1 minus P hat 2 is our best guess for the value of P1 minus P2. We can use our familiar formula to calculate a confidence interval for P1 minus P2. That statistic plus or minus the critical value times the standard deviation of the statistic. When the 10% condition is met, the standard deviation of the statistic of P hat 1 minus P hat 2 is this right here. We've seen that already. If our normal conditions met, we can find the critical value Z star for a given confidence interval from the standard normal curve. We will do that the same way that we've done it before for the critical value. It is a z-value because we're dealing with proportions. You can imagine where we're going with this, but with means, it'll be a t-value. All right, so conditions for constructing a confidence interval about a difference of proportions. Make sure it's a randomized experiment or random samples have been taken. 10% condition needs to be met. And the large counts. We've already checked the large counts with that previous example. Because we're assuming the populations are 2,000 or more students at both high schools, the 10% condition would be met. And we're told it was simple random samples. So all those conditions met for the previous example. Because we don't know the values of the parameter P1 and P2, we replace them in the standard deviation formula with the sample proportions. And that result comes out to be this. When the conditions are met, an approximate C% confidence interval for P hat 1 minus P hat 2 is the quantity P hat 1 minus P hat 2 plus or minus Z star times the square root of all this right here. Where Z star is the critical value from the standard normal curve with C% of the area between negative Z star and positive Z star. Okay, you'll find that the same way we did before with confidence intervals. Now, that's been a couple chapters ago. We've been in significance test mode here recently. So remember, if you're looking for a Z value, you're going to use inverse norm. Okay, it's the inverse ones when we want a value from that curve, because the area of the curve is that middle area right there. Now, of course, we have to figure out the area to the left. You recall how we did that with 95% in the middle. That means 5% is on each. 5% would be on the ends. So you have to figure out what's half of that to figure out what's on the left side. So in that case, 0.025. 90%, you have 90% in the middle. So you got 10% on the ends, so 5% on each end, 0.05. And then 99% in the middle, that means you got 1% on each end, so that means a 0.5% on each end, that's 0.005. All right. Significance tests for P1 minus P2. An observed difference between two sample proportions can reflect an actual difference in the parameters, or it may just be due to chance variation in random sampling or random assignment. Significance tests help us decide which explanation makes more sense. The null hypothesis has this general form. P1 minus P2 equals the hypothesized value. We'll restrict ourselves to situations in which the hypothesized difference is 0. Then the null hypothesis says there is no difference between the two parameters. That means that P1 minus P2 is 0. Or even alternatively, you can write it as P1 equals P2. Now, all they did right there is they added P2 to both sides of that equation. That's how they got from this first one to the second one. Now, you could see it written either way. I gravitate more writing it myself towards the left, but nevertheless, you can actually write it this way on the right as well. It means the same thing. The alternative hypothesis will say there is some kind of difference we expect. That means that P1 minus P2 would be greater than 0, less than 0, or P1 minus P2 would be not equal to 0. Alternatively, those can also be written as P1's greater than P2, P1's less than P2, or P1 is just not equal to P2. If you want to alternatively write those the same way that they wrote this one up here. All right, significance test for P1 minus P2. You have to check the conditions. I think we've already went over those enough times now that you do have to make sure the 10% condition is met for both. I didn't say this earlier, but make sure the 10% condition is met for both populations. That is, N1 is less than or equal to a tenth of capital N1, and N2 is less than or equal to 1/10 of capital N2 for both populations. To do a test, we standardize P hat 1 minus P hat 2 to get a Z statistic. That test statistic will be the statistic minus the parameter divided by the standard deviation of the statistic. If that is true, if the null is true, the two parameters are the same, we call their common value P, and we need a way to estimate P, so it makes sense to combine the data from the two samples. This pooled or combined sample proportion is the count of successes in both samples combined, x1 plus x2, divided by the count of individuals in both samples combined, n1 plus n2. That's your p hat c. That's the combined one. You're combining the data from both sets of data, okay, from both samples. Suppose the conditions are met. To test that hypothesis, first find the pooled proportion p hat c of successes in both samples combined. Then compute the z-statistic. That is z-statistic is p hat 1 minus p hat 2 minus 0 all over the square root of p hat c times 1 minus p hat c all over n1 plus p hat c times 1 minus p hat c all over n2. So to find the p-value by calculating the probability of getting a z-statistic this large or larger in the direction specified by the alternative hypothesis. We use that. Remember, we use that z-statistic. We do a normal CDF. Depending on the direction, will tell us what tail we're doing it on, whether it's our upper bound or our lower bound, or if we have to do one and then double it to get both, we have to make sure we do that. The only thing new here that's kind of different is having to do this pooled proportion here, p hat c. That's what's kind of different. Of course, you find that by combining both samples. Take your number of successes in both samples. So if you had in the homework example, that would be the if we did a simple or that would be however many students at school 1 did their homework plus however many students at school 2 did their homework, all divided by the total sample size. So however many you sampled, that would be the 100 plus 200. It would be 300 total sampled based on that example from the counselors. However many they found in the first school plus however many found in the second school that did their homework out of those samples of 100 and 200 respectively. All right, so inference for experiments. Many important statistical results come from a randomized comparative experiments. Defining the parameters in the experimental settings is more challenging. Most experiments on people use recruited volunteers as subjects. When subjects are not randomly selected, researchers cannot generalize the results of an experiment to some larger population of interest. Researchers can draw cause and effect conclusions that apply to people like those who took part in the experiment. Unless the experimental units are randomly selected, we don't need to check the 10% condition when performing inference about an experiment. Okay, of course, remember the 10% condition is really for sampling. You don't have to do that in a randomized experiment. But if they are randomly selected, the units are randomly selected, then you have to check the 10% condition. All right. And there you go. So we'll have a day tomorrow where we're going to work on this some and work on some of the problems that go with this section. But hopefully this has been helpful. Thank you all.